In this section, we want to talk about what does dimension mean for any vector spaces. So let's begin with this theorem. So suppose that you have a vector space V and B be the basis for the vector space, and say the number of vectors in the basis to be n, then any set in V containing more than n vectors must be linearly dependent. So let us sketch the proof to see some ideas for this theorem. So first of all, let us form a set of p coordinate vectors. So here, p is a bigger number than n, such that all coordinate vectors live in Rn. Then this means that there exist non-trivial solutions to the homogeneous equation formed by these coordinate vectors because it has more columns than the number of rows, right? Because p is the number of column and n is the number of rows. Then second, so having non-trivial solutions to the vector equation means that those vectors in Rn is linearly dependent. And lastly, we have seen that there is a linear transformation from the coordinate vectors to p vectors in V, which is to take the square bracket sub b. So this tells us that we have non-trivial solution to the original homogeneous vector equation, or this tells you that those p vectors are linearly dependent. So basically, what we are using here is, so we are using the fact that the vector space V is isomorphic to Rn. And also, Theorem 6 states that if a vector space V has a basis on n vectors, then every basis of V must consist of exactly n number of vectors. So basically, this gives us an invariant of the vector space V. So now we can define what it means for the dimension of the vector space. So suppose that V is spanned by a finite set, then we call that V is finite dimensional vector space, and the dimension of V, which is denoted by dim of V, is the number of vectors in a basis for the vector space V. And if V is not spanned by a finite set, then we call V to be infinite dimensional vector space. So let's see some examples here. So dimension of the zero vector space has to be 0, and this is by definition. And the dimension of R to the n has to be n, because we have n standard unit vectors as the basis for Rn. And the dimension of p sub n equals to n plus 1, and this is because it has the basis, the standard basis given by 1, t, and so on until t to the n. And the dimension of p is infinite because the basis for the set of polynomials should be 1, t, t squared, t cubed, and so on, and we can go this until the infinite. And this set has an infinite number of vectors as the basis. Now, let us consider a subspace of R4, which has general element given by this, and we want to find the basis and the dimension of this subspace. And remember that the dimension is defined as the number of basis vectors. So to begin with, let's first identify the basis for the subspace W. So from here, if you separate each variables, then this gives you A times, I guess, 1, 2, 0, 3, plus B times, well, it should be 1, 2, 1, 0, plus C times 2, 4, 1, 3, plus D times 0, 1, 1, 1. So basically W is spanned by these four vectors. So we have to see whether these four vectors are linearly independent. So to see the linear independence, let's build a matrix A with these four vectors. So A is defined by 1, 2, 0, 3, 1, 2, 1, 0, 2, 4, 1, 3, and 0, 1, 1, 1. So how do we find the linear independence for the column vectors of A? Well, we have to take the RREF of this matrix. Then this will give you 1, 0, 0, 0, and 0, 1, 0, 0, and 1, 1, 0, 0, 0, 0, 1, 0. And the essential vectors are pivot columns, which is given by first and second and the last column. So for this reason, we can get rid of the third column, because if you add these two, then you will get this one. So from here, we can tell that, well, the set of these three vectors, 1, 2, 0, 3, and 1, 2, 1, 0, and 0, 1, 1, 1 is a basis for W. And this implies that the dimension of W equals to 3. So basically, we can classify all the subspaces of Rn by using the dimension. So for example, let's consider subspaces of R3. And I think we classified all the subspaces in previous chapter. So basically, the first thing that appears has to be zero-dimensional one, which is simply the zero vector space. And the one-dimensional subspace is any space spanned by a single vector. Or equivalently, we have seen that it forms a line passing through the origin. And two-dimensional subspace is any space spanned by two vectors, or that gives you a plane passing through the origin as well. And lastly, it has three-dimensional subspace, which is given by R3 itself. So suppose that H is a subspace of a finite dimensional vector space V, then any linearly independent set in H can be expanded to a basis for H, and as a subspace of V, the dimension of H has to be smaller than equals to V. So for example, like if you have R3 as the vector space V, and let's say H to be a plane that passes through the origin, so something like this. So if you take any vector V inside H, then V itself is linearly independent. Then you can expand V to a basis for H by adding another vector, W, such that that makes the set V and W spans the given subspace H. So let's look at this example. Suppose that H is given by span of these two vectors, which is a subspace of R3. So in this case, we have m equals to 3 because the vectors in H consist of 3 entries. However, the dimension of H equals to 2 because the number of basis vectors is 2. And for G given by span of these three vectors, then we know that these two vectors are linearly dependent. So this one is a redundant vector. And then we can tell that the dimension of G equals to 2 because this one is not a multiple of the other vector. The basis theorem states that for p-dimensional vector space V, any linearly independent set of exactly p elements in V is automatically a basis for B. Or vice versa, like if you find any p element that spans V, then that set automatically becomes a basis for V as well. So the point of this theorem is that, well, if you find a set of vectors that has exactly the same number of vectors as the dimension of the vector space, then we only have to check whether the set is linearly independent or it spans the whole vector space V to guarantee that the set is the basis. So let's use the theorem to show that the given set is the basis for P2. So we know that the dimension of P2 equals to 3, and this number matches with the number of elements in the given set over here. So let us show that the given set is linearly independent. So consider the homogeneous equation, say AT plus B times 1 minus T plus C times 1 plus T minus T squared equals to 0. If you distribute all the numbers into the parentheses, then that gives you negative CT squared plus, I guess, C minus B plus A times T plus C plus B equal to 0. Well, equivalently, this gives you C equals to 0, and C minus B plus A equals to 0, and B plus C equals to 0. So this too gives you that B equals to 0. Or equivalently, if you plug all this thing into the second equation, then you get A is 0 as well. Or in other words, the equation star has only trivial solution. This tells you that the given set B, that consisting of T 1 minus T and 1 plus T minus T squared, is linearly independent. Or if you use the theorem 9, the basis theorem tells you that the given set B is a basis for P sub 2. So the idea here is, again, if you have a p-dimensional vector space, then to determine whether the given p vectors is a basis for B, we only have to verify either the set of vectors is linearly independent or the set spans the vector space V. Now, let's talk about the dimensions for the null space and the column space of A. So basically, the dimension of null space of A was, so we've seen that the null space is spanned by the vectors associated to the free variables for the matrix equation AX equals to 0. So the number of the basis element equals to the number of free variables in the homogeneous equation AX equals to 0. And the dimension for the column space, well, we know that the basis for the column space was the vector associated to the pivot columns, right? So this corresponds to the number of pivot columns in A. So let's see these two things from the following example. So suppose that A is given by 2 by 4 matrix, something like this. Then finding the null space of A is equivalent to solving the homogeneous matrix equation AX equals to 0. And to solve this, we have to find the RREF of the given matrix A, which is given by 1, 2, 3, 4, 2, 4, 7, and 8. And this is row equivalent to 1, 2, 3, 4. And I guess it should be 0, 0, 1, and 0. And again, it is row equivalent to 1, 2, 0, 4, 0, 0, 1, 0. And this gives you x3 equals to 0, and x1 plus 2x2 plus 4x4 equals to 0, or x1 equals to negative 2x2 minus 4x4. So x equals to negative 2x2 minus 4x4, x2, and 0x4. Or if you separate these variables, then you get x2 times negative 2, 1, 0, 0, plus x4, negative 4, 0, 0, and 1. And we know that the spanning set of the null space of A are automatically linearly independent. So we can tell that the dimension of the null space of A equals to 2. And here you want to note that x2 and x4s were the free variables for the solution set of the given homogeneous matrix equation. And from RREF of A, we know that the first and the third columns are the pivot columns of A. So the basis for the column space should be the first and the third column of the given matrix. So the column of A is given by the span of, I guess, 1, 2, and 3 and 7. So we can tell that the dimension of column space of A equals to 2. And this matches with the number of pivot columns of A. To summarize this, the dimension of null space is the number of free variables in the equation AX equals to 0. And the dimension of the column space was given by the number of pivot columns. But note that pivot positions correspond to the basic variable for the homogeneous equation. Then we can observe that, well, if you add the dimension of the null space and the dimension of the column space, so the first one corresponds to the number of non-pivot columns, and the second one corresponds to the number of pivot columns. So we can tell that this equals to the number of columns of the given matrix A. So we will explore these kind of relationship in the following section.